Types of filters and their function and its application. Filters are used across many fields to remove or isolate specific elements from a set, whether it's data, light, sound, or substances. Here are some common types of filters, categorized by their applications. A low-pass filter, LPF, is a type of electronic or signal filter that allows signals with a frequency lower than a certain cutoff frequency to pass through and attenuates frequencies higher than the cutoff. This type of filter is commonly used in audio processing, signal processing, and electronics to reduce high-frequency noise or to shape signals. Key concepts. Cutoff frequency. This is the frequency above which the filter starts attenuating the signal. Frequencies lower than this value pass through with minimal or no attenuation. Attenuation. High-frequency components above the cutoff frequency are reduced or blocked by the filter. The rate at which they are attenuated depends on the filter's design. Passband and stopband. Passband. Frequencies below the cutoff that are allowed to pass through. Stopband. Frequencies above the cutoff that are attenuated. Transition band. The range between the passband and stopband where the attenuation gradually increases. This is especially relevant in analog filters. Types of low-pass filters. Analog low-pass filter. Built using resistors, capacitors, and inductors in analog circuits. RC, resistor-capacitor, filter. A simple low-pass filter that uses a resistor and capacitor in series or parallel. LC, inductor-capacitor, filter. Uses an inductor and capacitor, commonly in higher power applications. Active filter. Uses operational amplifiers, op-amps, with resistors and capacitors for more precise control over frequency characteristics. Digital low-pass filter, implemented in software using algorithms, allowing for more flexibility in frequency response shaping. Moving average filter, simplest form of digital low-pass filter, averaging a set of data points. Finite impulse response, FIR, filter, a more advanced filter with adjustable frequency response. Infinite impulse response, IR, filter, more efficient, often used when real-time processing is necessary. Applications of low-pass filters. Audio processing, to remove high-frequency noise from audio signals, creating smoother sound. Image processing, to blur images or reduce high-frequency details, making edges less sharp. Radio and communication systems, to limit bandwidth in transmitted signals, ensuring only the necessary frequencies pass through. Data smoothing. In sensors and measurement devices, low-pass filters are used to smooth out rapid changes in data, such as noise or sudden spikes. Control systems. Used in systems requiring smooth output, such as motor control and robotics, to prevent abrupt changes in command signals. The simplicity of the RC low-pass filter makes it popular for audio and signal processing applications where high frequencies need to be reduced. A high-pass filter, HPF, is a type of electronic or signal filter that allows frequencies higher than a certain cutoff frequency to pass through, while attenuating frequencies lower than this cutoff. This type of filter is useful for eliminating unwanted low-frequency signals, like DC offset or noise, and is commonly used in audio processing, communications, and electronics. Key concepts. Cutoff frequency, the frequency at which the filter begins to attenuate signals. Frequencies above this point pass with minimal or no attenuation, while those below it are increasingly reduced. Passband and stopband. Passband, frequencies above the cutoff frequency that are allowed to pass. Stopband, frequencies below the cutoff frequency that are attenuated. Transition band, the range where the signal begins to transition from the stopband to the passband, showing a gradual increase in signal passing. Attenuation rate determines how rapidly frequencies below the cutoff are reduced. This rate depends on the filter's design, often specified in decibels per octave, dB/octave. Types of high-pass filters. Analog high-pass filter, built with resistors, capacitors, and inductors in analog circuits. RC, resistor-capacitor, high-pass filter. A simple circuit made with a resistor and capacitor, where the capacitor is connected in series with the input signal and the resistor is grounded. LC, inductor-capacitor, filter, used in applications that require higher power, using an inductor and capacitor to create the high-pass effect. Active high-pass filter, uses operational amplifiers, op-amps, in addition to resistors and capacitors to provide better control over frequency characteristics and allow for amplification. Digital high-pass filter. Implemented through algorithms and software, ideal for more precise or adaptive filtering. FIR, finite impulse response, high-pass filter, provides stable and precise control over frequency response. IR, infinite impulse response, high-pass filter, more computationally efficient, but with a less precise frequency response, often used for real-time applications. Applications of high-pass filters. Audio processing. Removes low-frequency noise, e.g., hums and rumbles, and DC offset in audio signals, making sound cleaner. Image processing. Enhances edges and fine details by blocking low-frequency content, often used for sharpening images. Communication systems. Filters out low-frequency noise or interference in transmitted signals, allowing better quality transmission. Signal conditioning. Used with sensors to remove baseline drift or low-frequency fluctuations, isolating more meaningful data. Data smoothing. In data analysis, high-pass filters remove long-term trends or slow changes, helping highlight rapid changes in the data. Characteristics of high-pass filters. Slope. The attenuation rate, often 6 dB per octave for a simple RC filter, with sharper slopes achievable with more complex filters. Phase shift. Like most filters, high-pass filters introduce a phase shift in the signal, especially near the cutoff frequency. Practical considerations. High-pass filters are widely used in applications where low-frequency components are considered unwanted noise, or when isolating high-frequency information is essential for the signal's purpose. A bandpass filter, BPF, is a type of filter that allows frequencies within a specific range or band to pass through, while attenuating frequencies outside this range. Bandpass filters are widely used in applications where it's necessary to isolate a certain range of frequencies, such as in audio processing, communications, and medical devices. Key concepts. Passband. The frequency range that the filter allows to pass through with minimal or no attenuation. It is defined by a lower cutoff frequency and an upper cutoff frequency. Stop bands. Low-frequency stop band. Frequencies below the lower cutoff frequency, which are attenuated. High-frequency stop band. Frequencies above the upper cutoff frequency, also attenuated. Bandwidth. The width of the passband, calculated as the difference between the upper and lower cutoff frequencies. Center frequency. The midpoint frequency within the passband, often where the filter allows the maximum signal to pass through. For a bandpass filter, it is calculated as types of bandpass filters. Analog bandpass filter. Built using resistors, capacitors, and inductors in analog circuits. RC and RL filters. Simple bandpass filters created with resistor-capacitor, RC, or resistor-inductor, RL combinations, often used for lower frequency applications. LC filters. Inductor-capacitor, LC, bandpass filters are used for higher frequency applications, such as radio frequency, RF, circuits. Active bandpass filters. Use operational amplifiers, op-amps, along with resistors and capacitors for better control over frequency characteristics and gain. Digital bandpass filter. Implemented using digital signal processing, DSP, algorithms. Finite impulse response, FIR, filters. Provide precise control over the frequency response but require more computation. Infinite impulse response, IR, filters. Efficient and commonly used for real-time applications, though with less precision than FIR filters. Applications of bandpass filters. Audio processing. Isolates specific frequency ranges, such as a particular musical note or a vocal range, and removes frequencies outside that range. Wireless communications. Allows specific channels or frequency bands to pass while blocking others, enabling different signals to be separated in radio, TV, and cellular communications. Medical devices. Filters used in devices like ECGs and EEGs to isolate specific biological signals, e.g., heartbeats, brain waves, by filtering out other frequencies. Instrumentation and measurements. Used in scientific instruments to focus on signals within a certain frequency range, such as seismic data analysis. Optics. Optical bandpass filters allow only a certain range of wavelengths, frequencies, of light to pass through, used in photography, lasers, and scientific imaging. Example: Simple RC bandpass filter. A simple bandpass filter can be made by combining a high-pass and a low-pass filter in series, where the output of the high-pass filter feeds into the low-pass filter. This allows frequencies within the range to pass while blocking frequencies below and above the range. If you have a high-pass filter with a cutoff frequency, low, F, low, and a low-pass filter with a cutoff frequency, high, F, high, the bandpass filter will pass frequencies approximately between low, F, low, and high, F, high. Characteristics of bandpass filters. Steepness of roll-off. The rate at which frequencies outside the passband are attenuated, often determined by the filter order. Higher order filters have steeper roll-off. Phase shift. As with other filters, bandpass filters introduce a phase shift in the signal, especially near the cutoff frequencies. Q factor. High Q filters provide narrow bands, used for precise frequency isolation. Low Q filters provide wider bands, suitable for broader frequency ranges. Bandpass filters are invaluable for isolating specific signals in noisy environments, or when focusing on a narrow range of frequencies is essential. A bandstop filter, also known as a notch filter, is a type of filter that attenuates or blocks a specific range of frequencies, the stop band, while allowing frequencies outside this range to pass with minimal or no attenuation. This type of filter is used when a specific frequency range, often associated with noise or interference, needs to be removed from a signal. Key concepts. Stop band. The range of frequencies that the filter attenuates. In a notch filter, this range is typically narrow, focused on a very specific frequency, such as 60 Hz power line interference. Passbands. Low-frequency passband. Frequencies below the stop band that are allowed to pass. High-frequency passband. Frequencies above the stop band that are allowed to pass. Bandwidth. The width of the stop band, defined by the difference between the lower and upper cutoff frequencies. For a narrowband notch filter, this bandwidth is very small. Center frequency. The midpoint of the stop band, often the frequency at which the filter achieves maximum attenuation. The center frequency. Types of bandstop filters. Analog bandstop filter. Created using combinations of resistors, capacitors, and inductors. RC or RL bandstop filters. Simple bandstop filters that use resistors and capacitors, RC, or resistors and inductors, RL. LC filter. A higher performance bandstop filter using an inductor and capacitor, commonly employed for radio frequency applications. Active bandstop filters. Use operational amplifiers, op-amps, along with resistors and capacitors, allowing better control over the stop band and higher gain. Digital bandstop filter. Implemented using digital signal processing, DSP, algorithms. Finite impulse response, FIR, filters. Provide precise control over the frequency response. Infinite impulse response, IR, filters. Often used for real-time applications, though with slightly less control over the stop band sharpness compared to FIR filters. Applications of bandstop filters. Power line interference rejection, used to remove specific low-frequency interference, such as 50 Hz or 60 Hz power line noise, in sensitive audio or measurement equipment. Audio processing. Removes unwanted frequency components, such as feedback or hums, which can improve the clarity of audio signals. Medical devices. Eliminates noise from electrocardiograms, ECGs, electroencephalograms, EEGs, or other biosignal recordings by filtering out interference. Communication systems. Used to block specific interference frequencies while allowing the communication signal to pass, improving signal quality. Seismology. Filters out specific frequencies in seismic data, making it easier to isolate signals from natural events or other sources. Example. Simple RC notch filter. A simple analog notch filter can be designed using a parallel RC circuit in series with the signal path, with the goal of attenuating a specific frequency. Characteristics of bandstop filters. Attenuation depth. Specifies how much the filter attenuates frequencies in the stop band, with greater attenuation providing more effective interference rejection. Bandwidth. Determines how broad or narrow the stop band is. A narrower bandwidth is desirable when isolating a very specific interference frequency. Q factor. High Q notch filters are used when precise frequency rejection is needed, as they create a very narrow stop band centered around the unwanted frequency. Practical considerations. Bandstop filters, especially notch filters, are particularly useful when dealing with consistent noise at a specific frequency, such as AC hum or equipment-generated interference. Their ability to remove specific frequencies without affecting the surrounding signal makes them invaluable in both analog and digital signal processing. An all-pass filter is a type of filter that allows all frequencies to pass through with the same amplitude, but alters the phase relationship between different frequencies. Unlike other filters, such as low-pass, high-pass, and bandpass filters, an all-pass filter does not attenuate any part of the frequency spectrum. Instead, it modifies the phase shift, which makes it useful in applications where phase correction or phase alignment is required. Key concepts. Phase shift. The primary effect of an all-pass filter is to introduce a frequency-dependent phase shift. The amount of phase shift varies with frequency, often increasing gradually as frequency increases. Amplitude response. All-pass filters maintain a flat amplitude response, meaning they allow all frequencies to pass at equal strength, so there is no attenuation or amplification of specific frequencies. Group delay. Group delay is the rate at which phase shift changes with frequency. In an all-pass filter, group delay varies across frequencies, which allows for precise phase alignment of signals within specific frequency ranges. Pole and zero placement. The design of an all-pass filter involves strategically placing poles and zeros on the complex frequency plane to achieve the desired phase characteristics. By adjusting these placements, the phase shift at specific frequencies can be controlled. Types of all-pass filters. Analog all-pass filters, built using passive components, resistors, capacitors, inductors, or active components, operational amplifiers. First-order all-pass filter uses a single RC circuit and provides a phase shift up to 90 degrees across the frequency spectrum. Second-order all-pass filter uses a more complex circuit to create a phase shift up to 180 degrees, allowing for more precise control over the phase response. Digital all-pass filters, implemented in digital signal processing, DSP, using algorithms. Finite impulse response, FIR, all-pass filter. An FIR all-pass filter is challenging to design because achieving a true all-pass behavior with finite samples is difficult. Infinite impulse response, IR, all-pass filter. More commonly used in digital applications, as it can easily create an all-pass effect with fewer computations. These filters can provide precise control over phase shift with a manageable level of processing. Applications of all-pass filters. Phase correction, used in audio and communication systems to correct phase distortions that can occur from other filters or from the transmission medium. Group delay equalization. In audio processing, all-pass filters can equalize the group delay to ensure that all frequency components of a signal arrive at the output in phase alignment, which improves sound quality. Feedback control systems. All-pass filters can control phase without affecting amplitude, which is useful in control systems where precise phase adjustment is needed for stability. Filter design compensation. In cascaded filter systems, an all-pass filter can compensate for unwanted phase shifts caused by other filters. Psychoacoustics, sometimes used to create specific auditory effects by manipulating the phase of signals without changing their amplitude, enhancing spatial perception in stereo systems or surround sound setups. Example: first-order analog all-pass filter. A first-order analog all-pass filter typically consists of an operational amplifier, op-amp, with an RC network in the feedback path. The circuit achieves a phase shift that varies from 0 degrees to 90 degrees across the frequency spectrum. Characteristics of all-pass filters. Phase shift control allows for smooth, continuous adjustment of phase shift across frequencies. Flat amplitude response passes all frequencies with equal amplitude, preserving the spectral balance of the signal. Group delay manipulation controls the timing of frequency components, which is beneficial in signal alignment and timing correction. Practical considerations. All-pass filters are not used to alter signal strength, but are essential for managing signal timing and phase relationships, which is critical in fields like audio processing, control systems, and communications. By maintaining a flat amplitude response while adjusting phase, they offer unique solutions to phase alignment challenges. Digital filters are algorithms or processes used to manipulate or alter signals in the digital domain, commonly implemented in digital signal processing, DSP. They operate by processing discrete time signals, which are sequences of numbers representing sampled values of a continuous time signal. Digital filters are highly versatile and can perform a wide range of functions, including noise reduction, signal shaping, and frequency isolation. Key characteristics of digital filters. Sampled signals. Digital filters work on discrete data points obtained from sampling a continuous signal. Flexibility. Digital filters can be programmed to implement a variety of responses, making them suitable for highly precise, complex filtering. Stability. With appropriate design, digital filters can achieve stable behavior over time, a crucial factor in applications like communication systems and audio processing. Types of digital filters. Digital filters are primarily classified into two categories based on their impulse responses: finite impulse response, FIR, and infinite impulse response, IR, filters. Each has unique advantages and is suited to specific applications. 1. Finite impulse response, FIR, filters. Definition: FIR filters have a finite duration of response to an impulse input. They are designed such that once the input signal ends, the output signal also eventually stops after a certain number of steps. Characteristics. Linear phase response. FIR filters can be designed to have a linear phase, which preserves the waveform of the signal, making them ideal for audio and communication applications. Stable by design. FIR filters are inherently stable, as they do not have feedback loops. High order requirement. FIR filters often require a higher order, more coefficients, to achieve a steep cutoff, which can make them computationally intensive. Applications. FIR filters are widely used in audio processing, image processing, and applications where preserving the phase of the signal is important. 2. Infinite impulse response, IR, filters. Definition: IR filters have an infinite duration of response to an impulse input because they use feedback, meaning the output depends on both current and past inputs as well as previous outputs. Characteristics. Efficient computation. IR filters achieve a desired frequency response with fewer coefficients than FIR filters, making them computationally efficient. Potential for instability. Because of feedback, IR filters can become unstable if not carefully designed. Nonlinear phase response. Most IR filters have a nonlinear phase response, which can distort signals where phase preservation is important. Applications. IR filters are often used in applications where computational efficiency is critical, such as real-time processing in communications and control systems. Key parameters in digital filter design. Cutoff frequency. Defines the frequency where the filter starts to attenuate the signal. It is critical for defining the passband and stopband. Order. Higher order filters provide a steeper transition between passband and stopband, but require more computational resources. Sampling rate. The sampling rate affects the design and performance of digital filters, as the cutoff frequency is often defined relative to the Nyquist frequency, half the sampling rate. Filter coefficients. These values dictate the frequency response of the filter and are determined during the design process. Design techniques for digital filters. Window method. Often used for designing FIR filters, this method applies a window function, such as Hamming or Hanning, to a desired impulse response to create a filter with specific properties. Frequency sampling. This method involves sampling the desired frequency response directly and then calculating the filter coefficients. Optimization techniques. Some digital filters are designed using optimization techniques like the Parks-McClellan algorithm to meet specific criteria for passband and stopband characteristics. Bilinear transform. A technique used in IR filter design to convert an analog filter design into a digital one while preserving key characteristics like stability. Applications of digital filters. Audio processing. Digital filters are used to shape audio signals by reducing noise, enhancing specific frequencies, and applying effects like reverb or equalization. Image processing. Digital filters are used in image sharpening, blurring, and edge detection by applying spatial or frequency domain transformations. Communications. Digital filters isolate specific frequency bands, remove interference, and modulate/demodulate signals in radio, Wi-Fi, and cellular systems. Medical signal processing. Digital filters are used in devices like ECG and EEG to remove noise and isolate specific physiological signals. Control systems, used to filter noise from sensor data and to adjust signals to achieve smooth control in real-time applications. Advantages of digital filters. Precision. Digital filters can be designed with a high degree of accuracy and precision, ideal for specific applications. Reproducibility. Digital filters provide consistent and repeatable performance, unaffected by component tolerances or aging. Adaptability. Digital filters can be dynamically adjusted in real time, enabling adaptive filtering for applications where signal characteristics change. Disadvantages of digital filters. Computational load. Digital filters require processing power, which may limit their use in applications with limited resources. Latency. Some digital filters introduce delays, which can be problematic in real-time applications requiring immediate response. Sampling artifacts. If not carefully designed, digital filters can introduce artifacts, especially if the sampling rate is not high enough relative to the signal frequency content. Digital filters are an essential component in modern signal processing, offering flexibility and precision that analog filters cannot achieve. By tailoring the response of digital filters to specific applications, they play a crucial role across various fields, from entertainment to medicine to telecommunications.